Hello, welcome back, class. Today is going to be the last part of differential calculus, part 5. It's also the last type of application of differential calculus, namely optimization. In this lesson, we're going to look at the concept of optimization. Then we're just going to go over some essential skills and concepts that you require to be able to do the optimization, which will then be followed by two types of applications. The one I refer to as direct and the other one I refer to as indirect optimization applications. And as you got used to, it will then end up with an exercise worksheet for you to practice these skills. Let's start. Optimization is the process or the procedure of modeling a situation by means of a function. Okay. Then applying differential calculus to determine the most appropriate or the best input values for the situation, which can then be used to determine the required maximum or minimum output values for the situation. Let's look at some examples. These examples here are just examples. We're not actually going to solve them or completely. First one, determine the minimum and maximum dosage of a medication to be prescribed for a patient for a specific treatment. You know, if you're a medical doctor, you want to prescribe some medication for a patient, it's essential that you have to know the minimum dosage. That means if you prescribe too little, that medication might not have any effect for the patient. On the other side, if you prescribe too much, it might be detrimental to the health of the patient. Let's look at a freshwater aquarium. If the water in the aquarium is too cold, some of the fish or some of the plantation in there might not survive. On the other side, if the water is too warm, there might be other fish who might not survive. Determine the lowest cost for the production of an article. You know, in business and production, you have cost and you'd like to try to make your cost as low as possible. In other words, you want to find the minimum costs. See, we also use other words, not necessarily minimum and maximum. Then, let's look at example number 4. Determine the largest, in this case, maybe we could have also said the maximum volume of a container that can be constructed from a given quantity of material. Let's say you have a amount of material, a sheet of material, and you want to make a container out of that. You'd like to try to utilize as much of that sheet of metal to make the largest container. On the other side, let's say you want to have a container with a specific capacity. Then you'd like to use as little material or the least amount of material to make that container. So there's just a few examples. But before we can actually do these optimization problems, it's necessary for you to know that there are certain basic things or concepts that you require. The most essential and primary skill that you're going to need in this one is your differentiation rules and the different notations that we use. As you can see here we have the ddx notation, and I have a power, and let's differentiate that power. It becomes nx to the n minus 1. Then we're going to need some function concepts, and specifically trying to determine function values by substituting. Then, if there are going to be 2D or 3D shapes involved, the area, perimeter, and volume formula you need to know. Except for formulas for cones and spheres, these formula, if there's an application pertaining to a cone or a sphere, the examiner must provide you with those formula, right? But not requirement if any other shape is used there. Then obviously you're going to need some basic algebraic skills like products or expanding, factoring, basic factorization, substituting by elimination, and then simplification of expressions. This will inevitably involve solving either a linear or a quadratic or a cubic equation. And then always in these problems, there will be some calculator skills, and you need to make sure that you're not careless with the use of your calculator. Let's just get a little bit of an overview of what we've done previously. If we look at a cubic function, f, but here we want to look at a cubic function with a finite interval from a to t. See, we don't have an arrow to indicate that it starts at negative infinity or an arrow there to indicate it continues to positive infinity. We have a situation, it has some restrictions, there's some constraints involved here. Point P. What is point P? That's correct. Point P is a local maximum. And that local maximum, if we just look at that, we see we have a value associated with it. And what do we refer to that value? That's right, a critical value. And let's say the value there is x equal to b. Let's look at another point. If I look at point Q, this we said is the local maximum, but this one here is more, the value, the output value is more than this one. What do we refer to this one? You see, this is actually here that's right, the true maximum. Or we'd also refer to it as the absolute maximum. And there we have the value, the endpoint, which is x equal to d. Let's look at another point. Point S, which one is that? That's right, that is the local minimum. And that local minimum, I have a critical value, and let's see the critical value, let's name it C. So I have a critical value at x equal to C. Then there's another point here, and that point is point T. This is a local minimum. But you see at T here, we have output values which is less than that minimum. So T is actually the true minimum, or we also refer to it as, that's right, the absolute minimum. And that absolute minimum we get at the other endpoint of the interval, namely at x equal to a. What are the turning points again? The local and maximum points, P and S. Now at P, if I have to get the gradient at point T, the gradient of a tangent, the gradient of a tangent there would be, that's right, will be 0, which we can also refer to it as the first derivative equal to 0, right? And then at the local minimum, we also have the first derivative equal to 0. So to determine local maximums and local minimums, this is the key to what we're going to do to determine the first derivative and equate it to 0. Now, to do optimization, there's a general procedure, right? Sometimes you need all the steps, sometimes you don't need, depends on what is given in a question. Whenever there's geometric situations, if diagrams are not provided, it's advisable for you to draw a simple diagram there. Then, first of all, there are some given information, there's some constraints that are given. Then you have to determine an objective function, and it's important that this objective function must be in terms of a single variable. Then taking that objective function, we're going to apply calculus, and that we find the first derivative. Then that first derivative must be equated to 0. You still remember why? That's right. It's the gradient of a tangent at that point, and the gradient of the tangent there is 0. Then that obviously gives you an equation. So you have to solve that equation, and solving that equation will result in what we've referred to it in our cubic function sketching. That's right, the critical values. And these critical values can then be used to determine the required optimum value or values. But it's important in any problem, always read your question carefully, right? Because that will determine what you have to, what your final answer should be. Now let's look at some optimization applications. There are two types. I refer to the one as, and the other one is indirect. Let's see what the difference between the two of them would be. A direct application, in other words, you know immediately what you have to do. That will be where the objective function is given. So you can just start with your first derivative. An indirect application problem, the objective function is not given, right? So that objective function must be determined first before you can. Now let's look at direct application procedure, right? Because direct application procedure, as we said, what did we say there? The objective function is given, so we can immediately find the first derivative. What should we do with the first derivative? That's right, we have to equate it to 0. This then results in an equation. That's correct. And that equation, we'll have to solve it. And the value or values that we obtain are known as the critical values there. Then, once we obtain the critical values, we can determine the optimum value. And as before, what do I always emphasize with you? Always read your question carefully, right, to see that whether you are actually answering the question or not. Now let's look at some examples now, direct application examples. The first one, we have a production process or industrial process which requires water to flow through a cooling system. The rate R in liters per second at which the water is flowing through the system for a certain period of time, right? In seconds, so time is in seconds, is given by the equation. What do we say this should be? This is now our objective. Let's see what the question requires. Determine after how many seconds will the water be flowing at a maximum rate. So it's the rate, that objective function is given for it, and we have to optimize it. In this case, we need to find the maximum rate. Come. Before we actually do it, let's see whether you can recall the procedure. First of all, we take our objective function, which is given. First thing, that's right, we find the first derivative, right? Let's find the first derivative of that. Negative 0,4t plus 10, correct? What should we do with that? That's right, equate it to 0. So we get the derivative and we equate it to 0. This gives us a linear equation, which is very easy to simplify. It's embarrassing if you can't do that. So you transpose the 10 and divide by 0,4, and that gives us 25. Let's just see what the unit is here. Time, t is in, so it's 25 seconds. And what did we always say? Please read your question. Let's read the question. After how many seconds? There we've answered the question. T is equal to 25 seconds. Great. Let's proceed to another question now. A manufacturer has a capacity to produce 8,000 TV sets weekly. What does that mean, a capacity to produce? That's right. In other words, you can produce up to 8,000 or can produce less as well. So here we have a constraint, can produce between 0 and 8,000 TV sets. The profit P in rand earned if a number N TV sets are sold is given by that. This here again is our objective function. N is the number and P is in terms of the unit of South African currency, rand. Determine the number of TV sets produced weekly to maximize the profit. What needs to be optimized? The profit, right? And how do we go about that again? Come before we do it. Important procedure, objective function given. That's right, find the first derivative. That's right, equate it to 0. You still recall why it must be equal to 0. Then we get an equation and then we solve it. And what must we never forget? Read the question. Now let's see. There's the objective function. And here I'm using a different notation, dp dn, or you can say p prime as well. We differentiate that. That is negative 0,24 n plus 300, and we equate it to 0. Linear equation, very easy. Embarrassing if you get this wrong. 1,250. Let's read the question again. The number n, and that's what they just want, the number. So don't do anything unnecessarily there. Let's go to a third example. A particle moves along a straight line, right? Or an object moves along a straight line. A car moves along a straight line. Distance d in meters of a particle from a fixed point on the line at time t, so the time is in seconds, is given by. This again is our objective function given, so it's a direct application. Determine after how many seconds the particle will be closest to the fixed point. See, here I use another word, closest, another word for closest, nearest, right? You should know your English here. And instead of nearest, we say the minimum distance we want to find. Let's see again there, objective function. First thing we differentiate. Let's quickly differentiate that. See whether you can do it. That's correct. It is 40 minus 18 equal to 0. Again, a linear function. Easy. Solve for t and then we get that. Let's go back again. Don't forget, read your question. After how many seconds? T is equal. There we've answered the question. Okay. Let's look at the last direct application example. We have the surface area of a cylindrical pillar with a hemisphere on the top end that needs to be painted. The total surface area in meters squared is given by, so again we are given an objective function. Determine the value of the radius so that the least amount, in other words, least amount, lowest amount, or minimum amount. Let's see, can you visualize that situation? That's right, you can see there's a cylinder with a hemisphere, half a sphere on top there. And they both have the same radii. So, procedure again, objective function is given. Just be careful now with the derivative. Let's try that first before we show the result. That's correct. 2 pi r negative 1 comma 2 r to the, that's right, to the negative 2. And we equate it to 0. Now this is not a linear function. Let's be a little bit more careful. Let's transpose the negative 1 comma 2 r to the negative 2. And what is r to the negative 2? You can also write it as, that's correct, as 1 comma 2 over r squared. How can we solve this? There's a denominator. We can multiply both sides by r squared, or usually you just say, that's right, cross multiply. So I cross multiply. What's my objective? I want to find r. So to get r the subject, that's what I get there, right? And what would be the inverse operation for r cubed? Come, try again. That is the cube root of that. Now, calculator work, very easy. And then in this case, maybe it was required to give it in 2 decimal places there. Or if they say an exact value, then you just leave it in this form here. And as before, let's read the question. Determine the value of the radius. What did we find? We did find, so we've answered the question there. Now we're going to other examples. Same procedure as the direct, but just we're going to do something before we actually start with the differentiation. Let's go over the general procedure that will be applicable there. Read your question and you identify what is given, what the constraints are. Then you have to determine an objective function, and it's essential that that objective function utilize only a single variable. Then determine the first derivative like before. Then you equate it to 0, you get an equation, and then you can solve the equation. That will give you your critical values. You read your question, and that will determine you can use that to determine the optimum value or values. So let's look at this example now. Just looking at that, what do you see is missing there? That's right, no objective function is given. So this is an indirect problem. The sum of two numbers, in this case let's use x and y, could have said a and b. So what is the given information? What does sum mean? That's right, x plus y is 60. We have two variables here, x and y. Let's make one of them. In this case it's immaterial whether I choose x or y, it will be exactly the same. So let's go for y. Y is equal to 60 minus x. Objective equation. Now we have to see what's our objective. We want to maximize. What do we want to maximize? Let's read there. We want to maximize their product. What does product mean? multiplication. What do we, their product means the product of x and y. So that will be x times p for product, xy. But we don't want two variables. We can replace the y, and you can see here you need your algebra. Expand that, you get 60x minus x squared. Now let's start with the calculus now. Differentiate that, easy. 60 minus 2x, and we equate it to 0. Linear equation, easy. Don't be embarrass yourself by getting this wrong. X is equal to 30. Now, if we read the question, do we want x? Determine the two numbers. Numbers is plural. There's only one number. So you have to find the other number, and you can determine the other number by 60 minus 30. And remember, always make sure that you read. If you don't read, you might just have stopped there and you have overlooked that they want the numbers, not numbers. Let's look at this problem here. We have a rectangular plot as shown here. There's a rectangular plot, and it has an area of 600 meters squared. Come, quickly tell me what's the area formula for a rectangle. This is easy stuff, grade 5. Length times breadth, right? Determine the dimensions of the plot if the length of... Let's read this. What do they mean by dimensions? That's right, the length and the breadth, or in this case our x and our y. The length of fencing. What do they say there? To be completely fenced. What do they mean by completely fenced? If I put the fence there and the fence there and the fence there, have I completely fenced it? No way. I still have to do that part as well. So it goes right around. What do we call that measurement right around? Right? Perimeter. Peri means around. Meter means measurement. The measurement around. Right? So we want to minimize the measurement around there. Let's see now. So what is given here? Area equal to 600 square meters. Area is length times breadth. In this case, it's xy equal to 600. Two variables. Doesn't matter which one of the two I choose. Let's go for y. Y is equal to 600 divided by x. Now, what's our objective? We want to minimize the perimeter. What's the perimeter here? This formula you need to know. There's an x and an x and a y and a y. So it's 2x plus 2y, which we can write as 2x plus y. We want one variable. Remember that, one variable. So let's replace the y. And if we replace the y, we want to expand here. Let's quickly expand that. Let's see what you do. That's correct. It is 2x. 2 times 600 is 1200. But instead of over x, we rather write it in this form. Because if it's right like this, it will be much easier to differentiate. Let's use this notation here. dp dx. Or you could also use, what else could we use? P prime as well. So I have 2 negative 1200 x to the negative 2. That is equal to 0. Solve that. Be careful. This is not a linear. So we transpose. There we can. That's right. Cross multiply. Make x the subject. And here I have x equal to square root of 600. But remember, normally we say x squared is that. And you always put what in here? A plus or a minus. Why did I forget the plus or minus? That's right. X here. Let's see what is x is a length. A length cannot be negative. Distance are always positive values there. So don't put in the negative there. So you can either simplify it or keep it in third form. Again, if we read our question, we see we also want to obtain dimensions plural. So you need two values there, right? So always read. If you don't read, you might just stop there and then you think you've done. Let's look at a third example. We have a length of wire 50 centimeters and we cut it in two, and the emphasis here, unequal parts. Give me an example of how I could cut it. That's right, 10 and 40, 15 and 35, etc. 12 and 38. Okay, so we're going to cut it in two pieces. We don't know. We can try all the different ways of cutting it. But what does it say there? The one piece must be a square, as you can see there. and the other piece will be, so you bend it to form a square and you bend it to form a circle. Determine the length of each piece. So we want to determine the length. See how long, what's the length of each piece there, such that the sum of the area of the square and the circle will be maximized. So this area plus this area, the total area, needs to be maximized. Whether we can do that. There we have a length of wire. Remember, I'm cutting it. So I don't know how long I'm cutting the first piece. Let's say that's unknown. So let the length of the one piece be x. And let's use the x with the circle. Then we have the other piece, which is, that's right, 50 minus x. And let's utilize that with the square. What is the perimeter of a square? There, I just gave it to you. It's 4 sides. Perimeter. So that's perimeter, side, 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 side. So 4 sides make up the perimeter. So one side, if I know the total, one side will be, that's right, perimeter divided by 4. Right? What do we call the measurement around in a circle? We could say perimeter, but there's another word we use here. Come guys, you should be able to help us. That's right, the circumference. Okay, so we use the circumference, and the radius of the circle is r equal to the circumference. So I utilize the circumference, so it's x divided by the circumference. What's our objective? The sum of the areas. So area of the square, what's the area of a square? In this case, side squared. And the area of a circle, pi r squared. These are formula you must know. Then replace the s, and we replace the r, and you expand that. We're not going to, there's not enough space here to do the expansion. So after removing all those brackets, you know what you did here? 50 minus x over 4 times another 50 minus x over 4. X squared, and then that becomes 4 pi squared. And simplifying it, we eventually end up with that expression. I think an example like this, the examiner would say, show that that's the answer, in case you make a little bit of calculation errors there. So let's differentiate. Differentiate the constant. That's right, it's 0. Differentiate that, negative 0,25. Differentiate x squared. It becomes, and see, I just put the 2 there and the x there. That's again a linear expression. Transpose that, and then you just have to divide with a coefficient. And this is now, just be careful with your calculator work. We end up approximately 22. Then let's read the question. You want to determine the lengths. That's only the one length. So the other length will be 50 minus 2, which is 28 centimeters. I see I just left out the centimeters there. Just checking to see whether you are following me. Let's look at example number 4 now. We have an open box with a square base made from 900 square centimeters of material with dimensions as shown. Do you know what we mean by an open box? That's right. It doesn't have a top, right? Or it doesn't have a lid. You can see this box, it's open, you can see right through it. Right there you can see inside the box there. They said square base, there they tell us is x by x, and that is the height. So the 900 centimeters would actually be the what of the box? The surface area. How many surfaces do we have here? That's correct, 5, right? Because we don't have a top there. What's the objective here? We want to maximize the volume. Let's see. What is given? The surface areas. How many surfaces? 5. So there's 4 on the sides and a square in the base. 900. Which one would you make the subject here? Right? No, not the x, because that's x squared. Preferably the h. So h will be 900 minus x squared. To make x the subject would be a little bit more complicated. Always try to do the easier operation there. Objective equation. What's our objective? Volume. Volume of a box is? That's correct. Length times breadth times height. Length times breadth times height. In this case, x squared times h. Right? But we don't want to have two variables. So we just eliminate the h by substituting. And now we simplify this expression. That x can cancel with one of the x's there. 900 over 4, should do it mentally, don't mind using a calculator. That is going to be 225. And 1 over x, that really, it's embarrassing if you do that on a calculator. It's 0.25. So simplifying that, there we have an expression, objective function, that's ready to be differentiated. So let's differentiate that. Come, let's try that first. 225, that's correct. Negative 0.75 x squared. Lucky I can't see you. It would be embarrassing to see that you did that on the calculator. Solve for x. That's now a quadratic. We simplify that. And remember what we said about squares here? That's right. We need positive values only. Can get the value of x, but always remember to read dimensions, plural. So you need more than one answer there, right? That's always remember, read your question. Maybe I should put that read down here so you can remember that. Now let's look at another one. We have a cylindrical metal can having a volume of 300 cubic centimeters, right? So, and we need to make one like that. So there's the metal can that we have in mind. It has a radius and a height, and its volume, we want it to be exactly 300 cubic centimeters. Determine the dimensions. What dimensions mean? What are the dimensions here? The R and the H. Such that the cost of the metal to make the can, you're going to make this, so we need to know the surface area of the can. And the surface area, those are formula you need to know. Let's identify the volume. Volume is, that's correct, pi r squared h. That's 300. Which one now would you make the subject? That's correct, preferably the h. Then what do we want? What's our objective? Our objective is to minimize the surface area. So the surface area, how many surfaces does this metal can have? Yes, it has a top and a bottom. So that's a circle, 2 circles, and this is a formula you need to know in grade 12. But we only want one variable, so we have to eliminate the h, eliminating the h, right, and simplifying. And there we have the formula there, right? Maybe the question could maybe assist you and say, show that the surface area would be that. Let's differentiate. I like this notation, dA dr. So let's differentiate that. Now let's be careful then. You can see this is not linear, it's not quadratic. Let's transpose the negative. And what can we do? That's correct, we cross multiply. And preferably that r to the negative 2, write it rather as r over r squared. So it's much easier to use then. Again, r cube root. Take the positive, r is equal to, it'll just be a positive value anyway. So that's the radius. But the question says, that's right, determine the dimensions. So we've got the r, we still have to find the h value. That we find by substituting. And using your calculator, we obtain 7.25. Let's look at the, and remember, if you didn't read, you would have not have given us the value. Let's look at the second last question here. A right cone with a radius of r centimeters and height AB is inscribed in a sphere with center O. And a radius of 8 centimeters. You can see there's the radius of 8. Where else is the radius? There's the radius as well. That's also 8. Okay. There we use the word largest. And that is, instead of saying the, that's correct, the greatest or the maximum. Because this is a sphere and the question should provide you with these formula here, right? So there we have our diagram again. Calculate the volume. So you use the given volume formula, substitute the 8, and you just calculate that. Should be maybe not more than 2 marks, at most 2 marks there. Show that. Let's see, where's r? There's r and there's x. Now let's see now. We said this is a right cone, so this means this must be a right angle down here, right? If that's not a right angle, then this is not a right cone. So right angled, we have right angle triangle, and what do we associate that? Come, easy, that is a theorem of Pythagoras. So let's apply it, and let's just make r the subject, so that's r squared equal to 6. That should just be 1 mark there. And really embarrassing if you get that wrong. Determine the volume of the largest, greatest, the maximum. So we want a cone. You can see in that you can have a lot of cones. You can have very small ones, and if you shake it, it will make a noise there. But you want a cone, the biggest cone you can fit in there. So we're going to use the volume of a cone. That's a formula given. You can see we have the R. There's the R. And the H. What is the H measurement? 8 plus X, not 8X, 8 plus X. We expand that, and this is what we get after expanding. Now we're ready to differentiate. Differentiate 5120, differentiate that 64, negative 16, and that's correct, negative 3x squared. Equated to 0, what type of equation is this? Quadratic. We're not going to do all the different methods, factorization, using the formula, or you can just get it from your calculator. So x is equal to 8 over 3, and it must be a positive value here. Now let's read the question. Determine the volume. So you don't want x. We have to go further. What's the volume? You go back to your volume, right? And there's the volume formula that you had there, because you know the x value, right? You substitute, and be careful with your calculator work. You get this on the calculator. Just a little bit of advice. If you have something complex like this, calculate it, write it down. Clear your calculator and just do it all over again. Because so easily you could have made, if you get a different answer, then do it a third time. Okay? But really, you should not lose any credits for that. So we have to read the question, otherwise we would have stopped there. The last problem here. We have a figure alongside which shows a parabola. There's the parabola. You see, it's not a complete parabola. We have some restrictions here. There's some constraints. We only have the parabola drawn from 0 to 4. And there's some questions here. Look at that. There we have the diagram. We want the coordinates of B. What is coordinates normally? That's right, X and Y. What can the Y be? Y is our Fx value. What is Fx? It was given to us. 4 minus 0,25x squared. Show that the area, see here, they're giving you the area. So you just have to area of a triangle. That's right, half the, that's correct, OD times the height is BD. Let's do that. OD, what is OD? If we look at OD, OD is X. If we look at BD, BD is 4 minus 0,25. We then, now we want to optimize it as large as possible, the maximum. We differentiate it. There we've differentiated easy quadratic. Make x squared the subject and find the x value. Some simple calculator work. There's the exact value. It's an irrational number. 2,3. X is that. You see the question says value of x, so it's done. You don't have to go and work out anything further than that. Now, class, these are some 7 examples, and it covers most of the types of examples you could possibly get. Right? Now, to assist you, there's, as usual, a worksheet. If we look at the first one, is this direct or indirect? That's correct, it's direct because the objective is given. There's some scaffold questions. Again, another direct question here, right? Another direct question. Should see these questions here. No objective function. Yeah, you have to be a little bit more careful, right? I'm just giving you a little bit of a challenge here, but not. Then we have questions again, not a direct, with some guiding questions, or we refer to it as scaffolding. Then we have another one. You see, it guides you find the H. There it shows you, which surface area. If by any chance you make a mistake with that, just use this and continue with it, right? Then example number 7. Then example number 8, we're not going to go through. I want to give you a chance to read it on your own. Then we have example number 9. These questions came out of previous grade 12 external examination questions. There we have another one. Maybe you recognize that, just with some different values. And then we have something a little different. And then we have a cone and a sphere. I've left out the formula. I don't have enough space, but you can quickly look. 13, there's a question again with pertaining to a class. Thank you very much. I trust you will go through this, and that some of you will continue with calculus, yes, at university, right? It's very interesting. This is only the differential calculus. There's other calculus as well, and waiting for you to submit your questions regarding the 13 problems I've given to you. Thank you very much. Thanks.